Welcome to our deep dive into this world of model inversion attacks,
Right.
MIAs.
Right.
You've sent us this paper, and we're going to extract those core insights for you.
Excellent. Sounds fascinating.
It is. Now, given your expertise in machine learning, data science, and math,
Yeah.
this deep dive should really help you kind of refine your understanding of the vulnerabilities and also defense strategies in this domain.
Right. Yeah.
So this paper, it's called Model Inversion Attacks, a survey of approaches and countermeasures. It really dives deep into those mechanics of these MIAs, exploring how they can be used to reconstruct that sensitive training data from machine learning models.
Yeah, it really underscores the privacy risks with the increasing prevalence of machine learning models, across domains from image recognition and text processing to even graph analysis.
Oh, wow. Okay, so let's break down some of the fundamentals here.
Sure.
So the paper starts off with some formal definitions of MIAs and supervised machine learning.
Right.
So what do they say about that?
Well, it establishes that MIAs operate in the context of supervised learning, where a model learns to map input data to output labels. But the attack aims to reverse this process, using the trained model to infer, sensitive information about the original training data.
Okay, so it's kind of like if you're trying to figure out like the ingredients of a secret recipe just by tasting the final dish.
Precise.
That's kind of interesting.
Okay. And the paper introduces the concept of reverse hypothesis, a function that aims to map the model's output back to the input space, guided by some prior knowledge about the training data.
Okay.
Yeah.
And the paper also goes into the different levels of inversion, highlighting the varying degrees of information that the attacker might aim to recover.
Right.
What kind of stuff are we talking about here?
These range from recovering the entire training data set to extracting specific samples or even just inferring statistical properties of the data.
Oh, okay. So the severity of the attack depends on how much information they're actually able to extract.
Exactly.
Gotcha.
And to understand the diverse landscape of MIAs, the paper presents a taxonomy in Figure 2, categorizing attacks based on 3 key factors: method, access, and information.
Okay, let's unpack this taxonomy a little bit.
Sure.
Let's start with the method.
Okay.
So the paper distinguishes between these optimization-based and training-based attacks. What are the differences there?
So in optimization-based attacks, the attacker directly optimizes an input to produce a specific output from the model, effectively searching for an input that matches the desired target.
Okay, so it's kind of like trying to crack a safe by just trying different combinations until you find the one that unlocks it.
Yeah, kind of. While in training-based attacks, the attacker leverages the model itself to train a separate attack model, often using GANs.
Okay.
This attack model is then used to generate samples that resemble the original training data.
Oh, so it's more like you're creating a blueprint of the safes mechanism by studying how the original safe works.
Right.
Okay, very interesting.
Now, moving on to access, the paper differentiates between white box and black box attacks.
Okay. So white box, what does that mean?
In a white box setting, the attacker has full access to the model's parameters, architecture, and even the training algorithms.
So they know everything.
Pretty much. This provides them with extensive knowledge to exploit, making these white box attacks potentially more potent.
Yeah, definitely. So then what's black box then?
In a black box setting, the attacker only has access to the model's inputs and outputs.
Oh, okay.
So they're treating it as a black box.
So they don't know anything about it.
Not necessarily, but they have limited knowledge for sure. This limits their knowledge, but doesn't make the model invulnerable.
Yeah, they could still potentially figure something out.
Exactly.
Okay, and finally, you mentioned this information factor in this taxonomy.
Right.
Refers to the prior knowledge.
It does. It's denoted as that the attacker possesses about the training data.
Okay, so what kind of prior knowledge are we talking about here?
This prior knowledge can range from knowing the type of data used, like images or text, to having access to a subset of the training samples.
Okay, so that prior knowledge can really make a big difference in the effectiveness of an attack.
Precisely. The more they know about the training data, the easier it might be to reconstruct it.
Yeah, that makes sense.
Yeah.
Okay, now that we've established those fundamental frameworks of MIAs, let's dive into how these attacks manifest in different domains. Let's start with images.
Okay, sounds good.
So what's the deal with images?
The image domain has been a focal point for MIA research, with techniques evolving from basic optimization methods to sophisticated GAN-based approaches.
Okay.
Yeah.
the paper really highlights the use of jams for reconstructing faces from facial recognition models.
Right.
That's scary.
It can be. Early methods like vanilla MI relied on optimization techniques to find images that matched the target output, but these often resulted in blurry or unrealistic reconstructions. The introduction of GANs really revolutionized image-based MIAs, enabling the generation of highly realistic and accurate reconstructions.
Wow. Okay, so what's an example of that?
For example, the paper discusses the generative model inversion attack, or GMI, which uses GANs to synthesize images that closely resemble the original training data.
Wow, okay. But the paper also points out the challenges of these training-based attacks, especially in adversarial settings.
It does, where the attacker's access to the model is restricted.
Right, yeah. So what happens in those scenarios?
In these scenarios, attackers might have to rely on techniques like model stealing, where they first create a surrogate model that mimics the target model before launching the attack.
Okay, so it's like trying to decipher a message sent through a secure channel by first intercepting a similar message and analyzing its encryption pattern.
Yeah, that's a good analogy.
Okay. The paper also discusses the use of explainable AI, or XAI techniques,
It does.
to enhance MIAs. What's that about?
By exploiting the interpretability features of XAI, attackers can gain insights into the model's decision-making process, potentially facilitating data reconstruction.
So it's like gaining access to the thought process of the model,
Yeah, kind of.
understanding which features are most influential in its predictions.
Exactly.
Okay, now shifting gears a little bit, let's talk about text data. How did these attacks play out in that realm?
Well, the paper explores how MIAs can target various natural language processing, or NLP, tasks,
Okay.
such as embedding generation, classification, and language modeling.
Oh, wow. Okay, so any text-based model is vulnerable.
That's right.
Okay. The paper discusses interesting approaches like reconstructing hidden prompts in language models.
It does, where an attacker aims to recover the specific prompts used to generate certain text outputs.
Okay, so like imagine someone being able to figure out the questions you asked a chatbot just by analyzing its responses.
Right.
That's unsettling.
Yeah, it can be. The paper also highlights how collaborative inference attacks can be launched in edge cloud scenarios,
Okay.
where multiple devices collaborate to infer sensitive information from a shared model.
Okay, so it's like a group of spies pooling their limited knowledge to piece together a complete picture of a secret operation.
Yeah, that's a good way to think about it. The paper also discusses the use of query-free transferable attacks,
Okay.
where an attacker can craft queries that transfer across different models trained on similar data.
So they can use it like over and over again.
Exactly, amplifying the potential impact of MIAs.
Oh, okay. So it's like finding a master key that can unlock multiple doors, even if they have different locks.
Right.
Okay. And finally, let's move on to the domain of graphs, which, this might seem less obvious,
It does.
but it's equally vulnerable to MIAs.
Right.
What's the deal with graphs?
The paper emphasizes that graphs are used to represent a wide range of sensitive information,
Okay.
from social connections to financial transactions,
Right.
making them attractive targets for attackers.
Yeah, for sure.
MIAs on graphs can have, far-reaching consequences, potentially compromising the privacy of individuals or even disrupting critical infrastructure.
Wow. Okay. So what kind of methods are used to attack this graph data?
The paper delves into various methods, including techniques that exploit model intermediate information or rely solely on node embeddings to reconstruct sensitive relationships.
Okay.
Yeah.
What are some examples of those methods?
One notable method is MNEA, which focuses on recovering graph topology from node embeddings, even without prior knowledge of the target graph.
Wow. So it's like reconstructing a map of a city just by analyzing the movements of people within it without ever seeing the city itself.
Right.
Okay, that's really interesting. So the paper also discusses attacks that target graph classification models.
It does, aiming to infer sensitive attributes of nodes or edges based on the model's predictions.
Okay, so it's like figuring out the demographics or financial status of individuals in a social network just by observing how the network is categorized by a machine learning model.
Exactly.
Wow, that's kind of disturbing.
It can be.
Okay, so these examples really highlight the diverse and evolving nature of MIAs in the graph domain.
They do.
And it underscores the need for robust defense mechanisms to protect sensitive graph data.
Definitely.
Okay, so that brings us to the next crucial aspect of our deep dive, Defense mechanisms. How are researchers fighting back against these attacks?
Well, the paper dedicates a significant portion to exploring defense techniques,
Okay.
categorizing them into training time defenses and inference time defenses.
Okay, so let's start with training time defenses.
Yeah.
What are those all about?
These aim to make models inherently more resistant to inversion during the training process.
Gotcha, okay.
One prominent technique is differential privacy, or DP, where noise is added to the training data or model parameters to obscure individual data points, while preserving overall statistical properties.
So it's like adding static to a radio signal to prevent eavesdropping, but still allowing the intended message to be transmitted.
Yeah, that's a good analogy. The paper discusses various implementations of DP,
Okay.
including DP-SGD, which applies DP during the stochastic gradient descent optimization process,
Okay.
and PAEE, which uses multiple teacher models to generate private labels for student models.
Okay. So besides differential privacy, what other training time defenses are there?
There's information restriction,
Okay.
where the model's access to sensitive information is limited,
Okay.
and deception techniques, where fake data is introduced to mislead attackers.
Oh, okay. So what's an example of that?
For example, the paper mentions NetGuard,
Okay.
a defense mechanism that uses GANs to generate fake data that misleads attackers, preventing them from accurately reconstructing the original training data.
So it's like setting up a decoy
Right.
to divert attention away from the real target.
Exactly.
Okay, clever.
Now, moving on to inference time defenses, these focus on protecting the model's outputs during deployment to prevent information leakage.
Okay, so what kind of techniques are used there?
The paper discusses techniques like output perturbation,
Okay.
where noise is added to the model's outputs to make it harder for attackers to infer sensitive information.
So it's like adding a layer of encryption to the model's predictions,
Right.
making them harder to decipher.
Exactly.
Okay. Are there any other inference time defenses?
There are. Data obfuscation, where the input data is transformed to make it less revealing.
Okay.
And embedding augmentation, where additional information is added to the model's embeddings to make them more robust to attacks.
Okay. So what are some examples of those being used?
For example, the paper discusses the use of adversarial training to make models robust against MIAs,
Okay.
where the model is trained on adversarial examples that are specifically designed to trigger inversion attacks.
Oh, okay. So it's like training a boxer to anticipate and counter an opponent's punches, making them more resilient in the ring.
Yeah, that's a good way to put it.
Okay. The paper also highlights the use of transfer learning-based defense,
It does.
where a model's architecture is modified to make it less susceptible to inversion,
Right.
and the addition of adversarial prompts to protect language models from prompt reconstruction attacks.
Exactly.
So it's like reinforcing the walls of a fortress to withstand siege attacks.
Exactly.
Okay, so it seems like the effectiveness of these defense mechanisms really depends on the specific attack scenario
It does.
and the characteristics of the data and model being protected.
Right, making it crucial to choose the right defense strategy for each situation.
Yeah, for sure, for sure. Okay, so that brings us to the final key aspect of our deep dive for this section, evaluation metrics. So how do we measure the effectiveness of these attacks and the robustness of defenses?
Well, the paper provides a comprehensive overview of evaluation metrics used to assess both the effectiveness of MIOs and the robustness of defense mechanisms, highlighting the importance of quantifying the performance of both sides.
So it's like having a scoreboard.
It is to track the progress of the game between attackers and defenders.
Okay, so what kind of metrics are we talking about?
The paper introduces general metrics like accuracy, recall, and precision, which are commonly used across domains to evaluate the overall performance of machine learning models.
Okay, so those provide kind of like a baseline.
They do, for understanding how well the model is performing its intended task.
Okay.
But the paper also stresses the importance of domain-specific metrics, which are tailored to the type of data being targeted and the specific goals of the attack or defense.
Okay, so those domain-specific metrics provide more nuanced understanding of how well the attacks are working and how well the defenses are holding up.
They do.
Okay, so what are some examples of these domain-specific metrics?
For example, in the image domain, the paper discusses metrics like PSNR, FID, and KNN distance, each capturing different aspects of image quality and similarity.
Okay.
So PSNR, or peak signal-to-noise ratio, measures the quality of the reconstructed image compared to the original.
Okay.
FID, or fresh inception distance, compares the statistical properties of real and reconstructed images.
Okay.
And KNN distance measures how close the reconstructed image is to its nearest neighbors in the training set.
Okay. So those are for images.
They are. In the text domain, the paper highlights metrics like BLEU, rouge, and perplexity, which are commonly used to evaluate the quality of machine-generated text and language models.
Okay, so BLEU and rouge.
Those are used to evaluate the quality of machine translations,
Okay.
comparing the generated text to human-generated references.
Okay.
And perplexity measures how well a language model predicts the next word in a sequence, reflecting its understanding of the language.
Okay, and what about for graphs?
And in the graph domain, the paper discusses metrics like AUC, average precision, and joint degree distribution, which are used to evaluate the performance of graph classification models and the accuracy of graph reconstruction attacks.
Okay, so AUC.
That's area under the curve, commonly used in classification tasks to measure how well the model distinguishes between positive and negative examples.
Okay.
Average precision is a summary statistic for the precision recall curve.
Okay.
And joint degree distribution measures the similarity between the edge distribution of the original graph and the reconstructed graph.
Okay. So it seems like the choice of evaluation metrics really depends on the specific attack scenario.
It does. And the goals of the attacker or defender,
Right.
There's no one-size-fits-all metric.
Right.
The key is to select metrics that are appropriate for the task at hand and that provide meaningful insights into the performance of both attacks and defenses.
Yeah, makes sense.
Yeah.
So by understanding these evaluation metrics, we can gain a more comprehensive understanding of the strengths and weaknesses of different attack and defense techniques.
We can, paving the way for more robust and secure machine learning models in the future.
Right. So we've covered a lot of ground in this first part of our deep dive. We've explored the fundamental concepts of MIAs, this taxonomy of attacks, and how these attacks manifest in different domains.
Right.
We've also delved into the various defense mechanisms researchers are developing.
We have.
And the evaluation metrics used to assess their effectiveness.
Exactly.
So this foundational understanding, this really sets the stage for, our exploration of the latest advancements and future directions in MIA research in the upcoming parts of our deep dive. So stay tuned.
Yeah, it'll be interesting.
Yeah, definitely.
Definitely.
Looking forward to it.
All right.
Okay.
So, So let's take a break and we'll come back for part 2.
Okay, sounds good.
Sounds good.
All right.
Okay. All right. So now that we have a solid grasp of the fundamentals of model inversion attacks, let's delve into the cutting edge of research in this field.
Yeah, I'm curious, what are researchers doing to stay ahead of these attacks, right? What are they looking at?
Well, the paper goes on to highlight the promising research directions that are shaping the future of both attack and defense strategies.
Okay.
In the realm of MIAs.
Gotcha.
Yeah.
So it seems like they're constantly pushing the boundaries,
They are.
exploring novel approaches to, enhance the effectiveness of attacks.
Absolutely.
And develop those more robust defense mechanisms.
Exactly.
So researchers are really thinking outside the box.
They are looking for innovative ways to protect that sensitive data from these, increasingly sophisticated attacks.
Yeah, I can imagine.
One promising avenue is leveraging techniques from cryptography
Okay.
and secure computation
Okay.
to design models that are inherently privacy-preserving.
That sounds fascinating. So how would those techniques be applied in the context of MIAs?
So one example is homomorphic encryption, which
Okay.
allows computations to be performed on encrypted data without decrypting it.
Oh, wow. Okay.
This means that sensitive data could be processed and analyzed without ever being exposed in its raw form, making it significantly harder for attackers to extract meaningful information.
So it's like, performing surgery without ever opening the patient's body.
That's a great analogy, yeah. Another area of interest is the development of robust certification methods
Okay.
that can provide formal guarantees
Okay.
about the privacy properties
Okay.
of machine learning models.
Gotcha. So it's like having a seal of approval from a trusted authority
Exactly.
that assures users that a model meets certain privacy standards.
Exactly. This would involve developing mathematical frameworks and tools
Okay.
to verify that models meet specific privacy criteria,
Gotcha.
such as differential privacy. Such certifications would not only enhance user trust, but also establish clear benchmarks
Right? Yeah.
for privacy-preserving machine learning.
Yeah, that makes a lot of sense. It would create a more standardized approach
It would.
to evaluating those privacy risks
Exactly.
associated with different models.
Exactly. Now, the paper also delves into the future of MIA research in the context of specific domains,
Okay.
recognizing that each domain presents, unique challenges and opportunities.
Right, yeah. So let's start with the image domain.
Okay.
What are some of the anticipated developments in that area?
So one trend is the growing use of deep learning techniques
Okay.
for both attacks
Okay.
and defenses.
Okay, so deep learning is being used on both sides.
It is. Attackers are leveraging, increasingly sophisticated deep learning models
Okay.
to generate more realistic and accurate reconstructions, while defenders are using deep learning to develop more robust defenses.
So it's like a deep learning arms race
It is.
with both sides constantly trying to outmaneuver each other.
Yeah, exactly. And as deep learning models continue to evolve, so too will the MIAs that target them. Another area of focus is the development of defenses that are effective against black box attacks.
Right, because those are more challenging to defend against.
They are.
Right.
They are, because the attacker has limited knowledge of the model.
Right, okay, yeah.
One promising approach is to leverage techniques from adversarial machine learning,
Okay.
which studies how to make machine learning models more robust to adversarial examples,
Okay.
which are inputs specifically designed to fool the model. By applying these techniques, researchers hope to make image-based models more resistant to MIAs,
Okay.
even when the attacker doesn't have full knowledge
Okay.
of the model's inner workings.
Okay, cool. So let's shift our focus to the text domain.
Okay.
What about text?
The paper highlights the growing concern over the privacy risks associated with language models.
Okay, yeah.
Especially given their ability to generate highly realistic and coherent text.
Right.
Yeah.
These language models have become incredibly powerful.
They have.
But with that power comes the potential for, misuse.
There is. And privacy breaches.
Right, for sure.
One area of active research is the development of techniques to detect and mitigate MIAs against language models.
Okay.
This includes exploring methods to identify suspicious queries or patterns of model usage
Okay.
that might indicate an ongoing attack.
Okay, so it's like setting up a surveillance system
It is.
to monitor the language model's interactions and flag any potentially malicious activity.
Exactly. Another direction is the development of privacy-preserving training methods for language models. This could involve techniques like federated learning, where models are trained on decentralized data sets, or differential privacy, which adds noise to the training process to protect individual data points.
So it's about building privacy into the very fabric
It is.
of how these language models are trained and deployed.
It is, exactly. Now let's move on to the graph domain. What does the paper say about the future of MIA research in that area?
Right, yeah, because graphs, they often represent complex
They do.
and sensitive relationships, making them, I think, particularly vulnerable to attacks.
Absolutely.
The implications of successful MIAs on graphs can be, they can be far-reaching.
They can.
Potentially compromising social networks, financial systems, or even critical infrastructure.
Absolutely.
Yeah, for sure.
One research direction gaining traction is the development of graph-specific defense mechanisms.
Sure.
Traditional techniques like differential privacy might not be as effective for graphs
Okay.
due to their unique structure and properties.
Okay, so researchers are looking for defenses that are specifically tailored to the nuances of graph data.
They are. One promising approach is to leverage the concept of graph anonymization, which involves modifying the graph to obscure sensitive information while preserving its overall structure and utility.
So it's like disguising the graph's identity,
It is?
while still allowing it to perform its intended function.
Exactly. Another interesting direction is the development of graph-based adversarial training methods.
Yep.
This involves training graph neural networks
Okay.
to be robust to adversarial perturbations,
Okay.
similar to what's being done in the image and text domains.
So it seems like the research on MIAs against graphs is it's drawing inspiration from other domains,
It is.
but also forging its own path,
It is.
developing techniques that are, specifically designed for those unique challenges of graph data.
Absolutely. That's a great observation.
Okay.
The interconnectedness of different research areas is driving innovation in this field.
Yeah. Okay. Now, Throughout our deep dive, we've discussed the various techniques and strategies employed by both attackers and defenders in this ongoing battle for data privacy.
We have, but what's really striking about this paper is how it underscores the dynamic nature of the threat. As machine learning evolves, so too do the techniques used to exploit it.
Yeah, that makes sense.
Yeah.
It's a constant game of cat and mouse,
It is.
with researchers developing new defenses only to have attackers find new ways to circumvent them.
Exactly. Take differential privacy, for example.
Okay.
It's a powerful tool,
Okay.
but it's not a silver bullet.
Right.
Attackers are already finding ways to circumvent DP defenses,
Wow.
prompting researchers to develop even more robust methods.
So it's a never-ending cycle of innovation and adaptation on both sides.
It is, and this highlights the crucial need for ongoing research and collaboration
Yeah,
to stay ahead of the curve in this rapidly evolving field.
definitely, yeah. It's a reminder that we can't afford to be complacent
We cannot.
when it comes to protecting sensitive data in the age of machine learning.
Absolutely. The stakes are high and the consequences of inaction can be significant. Now, before we move on to the concluding part of our deep dive, I want to touch on one more crucial aspect highlighted in the paper:
Okay.
the importance of awareness and proactive measures.
Right, so understanding the threat of MIAs
It's crucial.
is crucial for anyone working with sensitive data
Absolutely.
or developing these machine learning models.
It's no longer enough to simply focus on accuracy and performance.
Right.
We need to prioritize privacy and security from the outset.
Right.
We need to design models with privacy in mind, incorporating privacy-preserving techniques from the ground up. And we need to stay vigilant, constantly monitoring for potential vulnerabilities, and adapting our defenses as needed. It's a call to action for the entire machine learning community to adopt, a more security-conscious mindset,
Yeah,
and to prioritize privacy as a core principle.
definitely, yeah.
The future of machine learning depends on our ability to strike a balance between innovation and responsibility, ensuring that these powerful technologies are used ethically and securely.
Okay, so we've covered a vast landscape in this deep dive, from the mechanics of these model inversion attacks to the strategies used by both attackers and defenders.
We have. This exploration has illuminated the critical importance of privacy and security, especially in this rapidly advancing field of machine learning.
Yeah, for sure. So as we reach the concluding part of our journey, let's distill those key takeaways
Sounds good.
from this paper.
Okay, great.
So what are the main things we should remember?
Well, first and foremost, this deep dive really underscores the dynamic nature of the threat posed by these MIAs. As machine learning models become more complex and sophisticated, so too will the techniques used to exploit them.
Right, yeah.
It's a constant arms race, a relentless pursuit of vulnerabilities, and the development of countermeasures.
Yeah, makes sense.
So this emphasizes the crucial need for, ongoing research
Right,
and vigilance within the machine learning community.
for sure.
Staying ahead of the curve requires a proactive approach to understanding emerging threats
Right.
and
Okay.
developing robust defense mechanisms.
Yeah, definitely.
The paper also highlights the importance of a kind of a multifaceted approach to defending against MIAs. There's no single silver bullet solution.
Right.
Instead, a combination of strategies employed at different stages of the machine learning pipeline is necessary. This includes incorporating privacy-preserving techniques during training, implementing robust defenses at inference time, and rigorously evaluating the effectiveness of these measures using appropriate metrics.
Okay, so it's like, building a fortress.
It is, with multiple layers of defense, each designed to thwart different types of attacks.
Right, okay.
The paper also stresses the importance of collaboration across disciplines.
Okay.
Addressing the challenges posed by MIAs requires insights not just from computer scientists, but also from, ethicists, legal experts, policymakers, and social scientists.
Yeah, that makes sense.
Yeah.
To bring everybody together.
This multidisciplinary approach ensures that the development and deployment of machine learning models consider not only technical aspects, but also societal implications and ethical considerations.
Yeah, for sure.
Another key takeaway is the need for greater awareness and education about MIAs. Understanding the potential risks associated with these attacks is crucial for anyone involved in developing or deploying machine learning models.
Right, yeah, absolutely.
This awareness extends beyond the technical community, encompassing policymakers, industry leaders, and even the general public.
Okay, so it's not just people who are like really deep into machine learning. It's everybody.
It is, yeah.
Okay.
Ultimately, fostering a culture of privacy and security in the field of machine learning requires a collective effort.
Right. Yeah. Okay. So as we wrap up this deep dive, I want to leave our listeners with a thought-provoking question,
Sure.
inspired by the paper's insights.
Okay.
So given like the ever-increasing sophistication of both attack and defense mechanisms, what emerging research directions hold the greatest promise for developing truly robust and secure machine learning models?
Well, the paper hints at several promising avenues, including the development of hybrid defense mechanisms that combine the strengths of different approaches, like differential privacy and adversarial training.
Okay, interesting.
Another intriguing direction is the exploration of explainable AI, or XAI,
Hmm.
which aims to make machine learning models more transparent and interpretable.
Yeah, okay.
By shedding light on the inner workings of these models, we might be able to better identify and mitigate privacy risks.
Right, so we can see what's going on inside
Exactly.
and kind of make adjustments.
And furthermore, research into techniques that provide formal guarantees about the privacy properties of models, such as robust certification methods, holds significant potential.
Okay, cool. Well, this deep dive has been a really insightful journey through this complex world of model inversion attacks. We've explored the mechanics, the challenges, and the promising solutions that are shaping the future of privacy and security in machine learning.
I hope this exploration has equipped you with a deeper understanding of this, critical domain and inspired you to engage in this ongoing conversation about, responsible and secure AI development.
Yeah, absolutely. So thank you for joining us on this deep dive, and we encourage you to continue exploring this fascinating, rapidly evolving field as we collectively strive to build a future where machine learning empowers us without compromising our privacy and security.